In this video, I'm going to show my students how to handle application-style questions in the context of quadratics. Enjoy. Cool. Let's get this started then. Have you seen the curriculum for today, the fact that it's a review week?
No, I have not seen it.
Okay, that's fine. So basically, it just means we kind of just go based off of whatever the students want to have a look at. Granted, the start of every class is to field specific questions. So do you have any questions specifically coming into this?
No, I don't have any questions.
Not particularly? Okay, that's no worries then. So what I've got now is a screenshot. Hello, Nishal. Welcome to the call. So what I've got currently is the Cambridge books up, and we're just sort of having a look at where people are. So where are you guys currently at as far as your studies go?
Our school uses Jack Roundabout. Currently, we did linear and quadratics, and
Linear
I have my
quadratics.
sack for it tomorrow.
Oh, okay. So you do have a sax work tomorrow. Cool. Might be a good place to start then, linear quadratics. How about yourself, Nishal? Anywhere in particular you've got in mind?
Not necessarily. I'm more so just seeing the class in general and seeing where I probably should work on.
Sure. No worries at all. Okay, linear and quadratics then. So, Mohammed, when it comes to those topics, which in particular do you feel like you'd like to revise first?
Probably quadratics.
Makes sense to me. So, I mean, there's a couple of ways to go about it. Well, specifically the review chapter will cover everything. And what we've got in there are going to be extended response questions, tech active, and usually tech free in there, and multis. So when it comes to doing your SACs historically, or any mathematical tests historically, what do you tend to struggle with most? The extended responses or the tech frees?
Probably application questions and just silly mistakes.
Application specifically. Okay. Might be worth, maybe instead of going to the review chapter, then we could do 3L instead. Okay, let's have a look at that 3L quadratic models. So as far as application style questions go, there's only a few things to keep in mind. The main thing would be to make sure that you consider the real world applications of what you're handling here. So in the example 24, I guess maybe I should quickly double check. Can everyone see the screen share as I've got them?
Yep.
Okay, yeah. So I've got a screen share and I've got one for handwritten notes as well. The one that I'm currently talking about is the Cambridge book. So just seeing out if it's any issue trying to see those. Okay, so first example we have here is basically about a rectangular garden, and we're trying to maximize the area. It's a very common question to sort of maximize something when it comes to quadratics. Fundamentally, all we're trying to do here is find the equation that describes the variable of interest, or the quantity of interest, which in this case is area. We're going to try and get that into a single variable. Instead of having like an x and a y, or a width and a length, we're just trying to get it all into the same variable. So I think one thing I'll do before we go into this specific example is just sort of show you a framework for how you can handle these. So maximum/minimum problems. This is kind of what I was talking about before, which is you want to find an equation that describes whatever your quantity is with a single variable. You'd probably want to just draw a quick sketch of it, just to make sure you can see all the possible x values or all the possible y values for that function, keeping in mind real-world quantities. Most of the time, lengths, areas, that sort of thing, they can never go negative. So that's what this second portion is talking about here, maximal valid domain, making sure it only ever stays positive. Once you have that graph, you can pretty quickly observe where your maximum or minimum is. All you want to do is solve for the y value at that spot. In this case, we are talking about quadratics, so that's the same thing as finding the turning point of your quadratic. You have a whole bunch of methods to achieve that. You've got completing the square, you've got axes of symmetry. If you have x-axis intercepts, you could find the midpoint of those as well. There's basically whatever method suits your fancy. So let's have a look. In this case, we are just given some information, and the idea is that you would create your own little picture of what's going on there. So we have a rectangular garden, 20 meters total of fencing wire, and it's being used to fence 3 sides of the garden. There's already an existing fence involved there. And the idea is to calculate the maximum possible area that could be enclosed. So the way they've set this up in particular is to make sure that one of the lengths in there are already accounted for. That 20 meters total of fencing wire is not going to go towards that particular length of our rectangle. So one thing to do would be to quickly draw a picture. Now they've drawn it like already for us. It'd be a good idea to maybe explore how you would draw this yourself. So I'm going to go to the handwritten notes bit. Can everyone see that? Or maybe I'll just say, does anyone have any issues seeing that?
Yeah, I can see it.
And sing out in the chat if you have any issues at any point. Okay, so we're supposed to have a full rectangle, but one of them is already going to have a fence attached. So we'll just say F for fence, just to make sure that we don't account for that. Every rectangle is going to have lengths and widths. So the way I would personally write this out would be to have an L, W, W, and I guess you could call this an L as well, but because there's a fence that was already involved, you wouldn't really want to account for that one. From here, that gives you an equation for the area of this rectangle, of this garden. That's the thing we're interested in, right? It says calculate the maximum area. So we think about area, just any equation for area of a rectangle, it's going to be the length times the width. Now, the issue with this is we've used 2 letters to achieve that. Very hard to work with something that has multiple variables in the same equation. So we need to figure out a way to get one of those variables on its own. Based on the question that we have here, if you go back to the screen share, does anyone have any idea how you get a second, or find a way to rearrange this equation?
Should we sub in what we know?
Well, what do we know? What could we sub in? Is there any, go ahead.
Is the 10 minus x over 2, is that given?
Not given. So the only thing that's supposed to be given in this question is the information in the header there. And the only numerical thing that we have is that there's 20 meters of fencing wire total for those 3 sides of the garden. So think about how you might incorporate that information into an equation. Any thoughts?
No, I don't have any thoughts.
That's fine. So if you think about how you would do this like in real life, you've got 20 meters of wire and you would maybe put some posts out and you would just unwrap that 20 meters of wire around your fence posts, and then that would form the perimeter of your shape. So if you think about what shape we currently have on the handwritten bit, the only thing that we're responsible for wiring up would be the 2 widths and the length. So we can say that the sum of all of those lengths must be 20, or I guess 20 meters. There's 2 W's, there's 1 L. What we have here are 2 equations that have the 2 unknowns, or the same 2 unknowns. So because the equation that we care about is area, what we're going to try and do is rearrange the other equation that we have in terms of one of those variables, and then sub that into our area equation. The reason why is because we want to make sure we only have one variable in that equation. Any thoughts about that so far? Cool. So from there, it doesn't really matter which one you pick. I'm going to pick L just because it's the easiest to get on its own. You would simply do 20 minus 2W is equal to L, and go back to your area equation. So instead of writing L there, we can write 20 minus 2W. A equals 20 minus 2W in brackets W. You see now we only have one variable here, which makes this like any other equation. You've got a y, you got an x. Or in this case, you got an a and a w. You can leave it like this if you like. You will need to sketch this quadratic anyway, so my recommendation is to leave it like this because it does make it easier to sketch the quadratic. But that would be how you start this out, getting your area equation. Any questions about that so far?
No.
Cool. So the next step of our framework is to sketch this. Right, we want to understand what are all the possible area values over the given domain, or over a possible valid domain, and we just want to pick the biggest possible one. So if I were to try and sketch this function a of w, any thoughts how I would do it? Okay, I have to do a bit of revision for quadratics then. How about this? What if I rewrote it as 20w minus 2w squared? Does that seem more approachable? Could you sketch that instead?
Well, for the first one,
Mhm.
would you just do 2 and then, well, I don't know what W is, so
Mhm.
what would the turning point be? Would it be just 2, 0, or
So where did the 2 come from?
2 for, like, is the first one, is it not in turning, it's not in turning point form, sorry.
No,
Thought
not
it
in
was a
turning
turning
point
point
form.
form.
Yeah, this is factorized form. So what does factorized form tell you about quadratics?
Uh, so factorized form is so you can find the x values.
Yeah, x values. Cool. So we could even make this like just really nice and simple. Instead of saying a, I'll say y, and instead of saying w's, I'll say x. That way it looks exactly like what you might expect from anything else, just keeping in mind that y is going to be our area and x is going to be our width. So how do we sketch this? The factorized form tells you the x's, so if you wanted to get the x-intercepts, what might you do?
If I want to get that x intercepts, I'll divide 20 by -2.
Yeah, because you'd have 20 minus 2, or 20 minus 2x is equal to 0, 20 equals 2. Okay, so maybe a little bit different to what you suggested. This is basically null factor law. When you have it in a factorized form, what you want to do is equate both of those factors to 0 and then rearrange to get the x on its own. So one of them would be 20 minus 2x is equal to 0, in which case you'd have 20 equals 2x, x equals 10. And the other one's nice and simple. It's just x equals 0 because, well, that is the factor. So we know we cut through 0 and 10. The only question now is this a positive or a negative parabola? And if so, does that mean we go like up like that or down like that?
Um, it's a positive parabola, isn't it? I mean, it's a negative parabola
Okay, how do you know?
because it's -2.
Yeah, and that's even more clearer when you expand it out if you need to have a double check. So that's going to be what our graph looks like. Any thoughts on why I stopped on just this portion here? Why I didn't go further?
Is it because you're just trying to find those values?
So, I mean, kind of, yeah. You only care about those specific values. The reason why we care about those specific values is because if you think about what a and x actually are, a is area and x is a width. And so you want to make sure that you never make any of those go negative, because in the real world, no such thing as a negative length or a negative area. That's why we're going to cut that off early. So this gives us our area graph. We're trying to find the maximum possible area. Visually speaking, it's right there, whatever the tallest possible value is for the area. Okay.
Yep.
How do we find it?
Oh, sorry, the pen and paper. I can't see it anymore.
Oh, can't say it anymore.
Wait,
Interesting.
yeah, I just found it.
Yep.
So what was the question again?
Yeah, so we have our area graph now. We know what the maximum is that we're looking for. How do we get the value?
No idea.
Okay.
Is it subbing x as 0?
So if you sub x as 0, what you'll
And you
find,
get the y value, right?
yeah, so when
Or
you sub in an x value, you get the y value that corresponds to that x value, correct? But if you sub in x equals 0, you're talking about this spot down here, which will give you this y value. So when you sub in x equals 0, you're talking about the y-intercept, essentially. We're looking for this point all the way up here. And you can see it's going to be, well, I kind of gave it away. It's the midpoint of both of those spots. When it comes to quadratics, if they have x-intercepts, you can always find the x value of your turning point by finding the midpoint of your two axes intercepts. Is that all fair enough?
Yep.
Okay.
it's always the midpoint, right?
Yeah. So it's always the midpoint under the assumption that your quadratic does have x-intercepts, because some of them don't, right? Like if I have if I do another graph here and I have a quadratic up here, you can't really use that method because it doesn't actually have any x-intercepts. So if it does have it, great, use them. If it doesn't, that's when you would do stuff like axes of symmetry. So for this one here, you would have maybe x equals negative b over 2a. That will give you this x coordinate. If you've done calculus, which I'd be surprised if anyone has at this point, you would be doing the derivative and setting that equal to 0. Ignore that if you don't know what calculus is. And if you have turning point form, you can just look at the turning point form. So a bracket x take h squared plus k. Well, I guess at that point you would literally just use the k value. You don't even necessarily care about the h because you just want the y, not the x. Those are the methods you have available to finding turning points for quadratics. In this case, we've used the midpoint to get our x value. And so Nishal had the idea before, how do we then get the corresponding y?
So if you have the axis of symmetry, do you just sub it into the equation?
Yeah, you sub it into the equation. So we have our equation, y equals 20 take 2x times x. We're just going to replace every x in there with a 5 because we know that at x equals 5, we have y equals whatever it'll equal. Y equals 20 minus 2 times 5 times, whoops, let's get the brackets properly. 2 times 5 and then times 5 at the outside. Y equals 20 minus 10 times 5. Y equals 10 times 5, y equals 50. So that's going to give you a value of y equals 50. Just keep in mind that we used y and x to make life a bit simpler for us. In reality, these were a's and w's. So that y value that we just found was our area, right? Maximum area in this case is 50. Only thing you would do from here is, because it's a application style question, is you have to consider the unit. So if you look back to the screen share with the book on it, everything in here was in terms of meters. And so when you do meters times meters, length times width, you would get meters squared as your final area unit. Okay?
Yep.
I have just noticed I might have done a weird. Why do they have their graph from 0 to 20? What did I do wrong? It was 2L. I might have messed up the numbers early on a little bit. We still ended up getting 50 though, which is odd. Don't see. What did I do wrong? Oh wait, no, they just put in. Okay, yeah, they probably rearranged for W instead of L, and it will look a little bit different. So you can do either way, whether you rearrange for W, whether you rearrange for L. It's the same sort of idea, but your equation will look ever so slightly different if you do it. So their x is talking about lengths, whereas our x is talking about widths. That's why their x domain is a little bit different. Had me frightened there for a second. I thought I made a mistake. Okay, so in summary, we pretty much just followed this framework that I've outlined at the beginning. We started by creating an equation that describes whatever that we cared about. In this case was area, so we needed the area equation, length times width. What we needed to do was get it in terms of one variable though. We had a length and a width. We just want either a length or a width, which in this case, we can determine that with the additional information that's given to us. We're told 20 meters total was being used, hence that forms the perimeter of our equation. From there, we drew a sketch of our graph. We didn't necessarily need to know every key feature about it, just enough to sketch it and find our turning point, because that is where the maximum occurs. And then you just use whatever method you want to solve for that turning point. Is it clear enough how we handle these types of questions?
Yeah. Yeah.
Cool. Okay. So you can access these under the Quadratics section of the classroom. All these notes are already here for you. So I'd revise that, and you could even see some other examples here. In fact, I did a very similar example, but I didn't have a backing on the fence. So you can see I've even used 20 meters. So what are the odds of that, right? But I just didn't do the backing of the fence. So you can see a very similar sort of setup here, all written out. Slightly different result because there was additional fencing that was required. Sometimes the maximum of your function is not necessarily going to be a turning point though. So we're going to have a very similar question here, which is we're trying to fence off a garden with 20 meters of fencing wire. This time we care about the fact that the length of one of the sides cannot exceed 4 meters. Right now we have a restriction on our domain. So instead of being able to sketch it from 0 to 10, we can only really care about 0 to 4, right? And the reason why is because of this here. X is our length values, and A is our areas on the top. Clear enough why we have to cut it off early?
Yeah.
So when we have a restriction, we calculate the entire domain, but then we cut it off to at some point, depending on the restriction.
You don't have to do the entire domain. It's purely there because it's easier just to know your x-intercepts, and then you can draw the shape and just cut it off later. If you'd like, you can just do, x equals 0 because of the factor out the front here. And you could just calculate what is it at x equals 4. You could just do that immediately. But it doesn't take a lot of effort to look at this and see that x equals 10 is your other x-intercept. It's a personal preference thing, really. The main thing is that you have to understand that you only care about this portion here up until L equals 4. And so you look at that portion in your graph and you think, okay, what's this thing's maximum? Well, the new tallest point isn't a turning point per se, but it cuts off there at when L equals 4. So if you want to find this value, what do you think we do?
Do a substitute.
Yeah, sub in L equals 4. Nice and easy. So you replace all these L's with 4s, and in this case you're going to get 24 meters squared. So it's a rare example where your maximum won't be a turning point. It has come up though, and it may still come up just to throw you off, especially in SACs, because SACs are much more like targeted in the particular topics. Exams, this sort of stuff, it's about 50-50 whether or not you're going to get a turning point for your maximum or whether you're going to have to restrict your domain a little bit more. But okay, those are like the main types of questions that you'll get for application style things. Let's do a quick review. So this one, that's a little bit different. We'll come back to that in a bit. I sort of want to go through the Cambridge book and just sort of show you, hey, this is when you would use this sort of thing. This one we've seen before, it's fencing. This one, fencing again. This one, a little bit different. You already have the function this time, but it's still doing very similar stuff. It's still saying sketch your function over a given domain. It still wanting you to find the maximum of whatever that thing is, in which case you'd find the turning point or the largest value, whatever that happens to look like on your domain. The only thing that's a little bit different here is they've added this other question, which is, okay, I don't want you to find a maximum, but I want you to find when is it greater than 70, or 70 or more, which means greater than or equal to 70. So very quickly, I'll draw what I think this graph will look like, and we'll explain what's going on there. So this one is, if I expand that out, it's going to be minus 400 x squared plus 400x. Okay, that's a bit nasty. I believe from memory, without getting to too many details, you do to sketch this between 0 and 1, and it's a negative quadratic, so it'll look like this. So again, a very similar shape to what we had up the top in the handwritten bit. As far as what maximum efficiency should be, from memory, I think this was 100 up the top, because this is an efficiency rating. And so this question in particular, part D, is describing what would it take, what are the x values that would cause this to be 70 or more. If 100 is up here, 100 being our absolute maximum, what do we think it would take to get above 70? How might we go about solving that?
If 100 is our maximum and therefore our midpoint, wouldn't it just be 70% of the midpoint? So like 0.7 times 0.5?
Possibly. Hang on. So 0.5, 70% of this. I think that might only work if it was linear either side, because when you have a parabola, it has a different rate of change over time. Like you can see, as it gets further and further away, it gets steeper and steeper over time. I reckon if this was linear, that approach might have worked, because that assumes a constant rate of change over the interval, and you could apply that 70% to it. With quadratics, because it has that sort of flex to it a little bit, it's not quite like one-to-one like you're suggesting. But that is a novel way of going about it. I think it would work for linear, not quite for this though, unfortunately. So we think efficiency rating is on our y-axis, and we're looking for efficiency 70 or more. It kind of just means we want to be above this line, 70, above the line y equals 70, because the y values are our efficiency. So when I draw it like this, if we want to be above this line, what do you think we do now?
You sub in a number that's above that line.
Sub in a number above the line. So our function is in terms of x. The thing that we're trying to solve for are the x values that get us above that line. So I want to know what's this and what's this. That's what we're aiming for. So it's kind of like the reverse of what we did here. What we did here is we had an x value and we needed to get a y value. In this case, we know the y value we have to be above. We need to get an x value from that. How might we use a similar approach to solve this type of question?
Would we say y equals negative 400x squared plus 400x, and then we substitute y as 70, so we do 70 equals the x equation?
Yeah, precisely. Yeah, you'd sub in the y equals 70, because what that will do is it'll tell you, kind of like how if you sub in an x, you get the corresponding y at that spot. If you sub in a y, you get the corresponding x's, plural in this case, at that spot. Now, I believe this one would be tech active, so I'll just sort of bash that out on the CAS, and hopefully my initial assumptions were correct with what the graph actually looks like. You'd have a function, let's call it h of x, is equal to 400 bracket x take x squared. And then if you were to solve using the CAS, you would have h of x is equal to 70, solve for x, and yeah, this would have been tech active. So it's going to give you two square root answers. If you look at what those would be as far as x values go, they're going to be 0.22 and 0.77 respectively, which when you look at the actual graph makes a decent amount of sense. You know, we kind of eyeballed it, but 0.22 would be there, 0.7, whatever it was, will be there. So yeah, you would just sub in your y equals 70. That will give you the corresponding x values for those spots. So that gives you the x values there. The question is specifically saying determine the x values between which the efficiency rating is 70 or more. And so there's a slight nuance to how you actually present the answer. You have all the information necessary. How do you actually present that as a final answer if you know you want to find all the x values that give you 70 or more?
Would it be an inequality?
Yep, inequality works, for sure. What might you write then?
No, I'm not sure.
X is 22 less than or 0.22 less than or equal to X, which is less than or equal to 0.77.
Yep. Whatever the other, yeah, that was 0.77. Yeah, that's how you would give that. This, I guess technically, this isn't it doesn't say a number of decimal places, so really technically you would want to give the root answers instead. So you'd want to use the exact values that were given, but that's sort of splitting hairs at this point. Fundamentally, the only thing I want you to understand, or the main thing I want you to understand, is how you write that answer. You give it as an inequality, or I guess more specifically an interval, which means you could use inequalities, or you could use brackets, 0.22, 0.77, using square brackets because they are inclusive. So yeah, main takeaway for these kinds of questions is if you're looking for a specific x value and you know the y, you can get it. If you're looking for a specific x, well, whatever the opposite is of what I said, you can find it. As long as you have one of the x or the y, you can get the other value by subbing into the function. And if you need to create your function, well, that's what we were talking about before, which is use the information in the question to draw a little picture and sort of put all the information that's given to you in equations, rearrange, and solve from there. So that's one other nuance on there. If we go back to the screen share, question 4 is the same as the area equations, what we've done, nothing actually new there. This is the same sort of thing, but you're given the equation already. So because this one is CAS, it might be worth doing this one together actually as well. Okay, so I'm going to go to the handwritten notes, and all I'm going to do is start by just sketching that function that was given to us. Okay, zoomed in, nice. So we have 1 plus 3 over 5x minus 1 over 50x squared. Cool. We have our curve. We're told our domain is x greater than or equal to 0, and part A tells us to do it between 0 and 30. So we'll go a little bit above that just so we can see everything. But when it comes to our graph, just remember that it will be only between 0 and 30. Quick question, do you guys use this CAS or the other CAS, Casio?
I use this one.
This one?
Yeah, same.
Cool, okay. Nice and easy then. So if you're concerned about forgetting your actual domain, I would still set your window settings a bit bigger. What I would do is I would jump in here and I would set a domain on this. So that's just a control and equals button, and use this bar, and all you're going to do is set whatever the domain is that you care about, which in this case is going to be 0 to 30. 0 is equal to x less than or equal to 30. And that way you can see very clearly what's going on without having to worry too much. Okay, so the first question that's actually a question that requires us to do something is to figure out what's the maximum height reached by the ball. So I'll let you jump back and forth between screens, and someone can let me know how you might find maximum height. One good question to ask would be, what variable is being tracked? What variable is tracking the height? Where does height actually appear on our graph or on our equation?
Do we do minus b over 2a?
So that'll give you, I mean, yeah, that is one way of going about it. Yeah. So because you're trying to find the peak, right? Because height is d, and since it's a d equation, d is on our y-axis. And so if you are looking at this graph and you're saying, yes, the maximum height is in fact the peak of the parabola, then yeah, you could use the negative b over 2a to find the x and then get the corresponding y. Nice. And that will give you the maximum height. This being a CAS question, you don't necessarily need to do that because we have a CAS, but if you were to do it tech-free, then yeah, negative b over 2a would be probably the best way to do this one because it is a complicated equation. But with our CAS tools, actually, would I even recommend doing that? Because one of the disadvantages of the CAS tools, with the graphing thing anyway, is if you go to Analyze Graph and choose Maximum, so the third option, I should actually click it instead of using the shortcuts. This one here, the maximum. What you can do is sort of scroll back and forth. Where's my cursor? There it is. You click back and forth between the two values, and it will give you whatever the maximum is over that range that you've, or I guess domain, that you've highlighted. Now in this case it's come out fine, because 5.5 does appear to be an exact value. The problem I've seen before is it will only give decimals, and it's very hard to tell if that is an actual closed decimal or if it is in fact just what the value is. So my preferred approach is, once you know what the value is going to be, just double check that it is in fact that closed form value and not just a rounded value. The way that works is you take note of what your function is called. In this case, it's f4. Go back to the calculator menu. There's this button here called VAR that I'm kind of shadowing over. If you click that, it'll show you all the functions that you've defined, whether it be on the graphing tool or whether it be on your on the calculator tool. We're just going to bring that one up here, and just to show you, that's what we had before. There is a CAS tool in here that will show you the maximum of any function. I believe it's under the calculus menu, and it's here, function maximum. So my recommendation is to use this instead because this will give you the exact values. You click that, you put your function into it, you say comma x, and that will give you the x value for which there is a maximum. In this case, it is x equals 15. We did see that before, but this is more so if you had like a root answer instead. The CAS graphing tool wouldn't show you that. You then plug that back into your function because you don't want an x, you want a y instead. That's going to give you 11 on 2, which of course was in fact 5.5. So it's just a way to get it to exact where the graphing tool doesn't usually give it to exact. Well, it doesn't ever give it to exact actually. Clear enough?
Yep.
Okay. So that is the answer to BI. What is the maximum height? Height was a y value. we found our y value of 5.5. In this case, you would give it in terms of meters, because that's what the question has told you d is in terms of. If we go back to the screen share, we have double I. A fielder has caught the ball when it was 2 meters above the ground. How far was the ball from where it was hit? So we have a fielder, the ball has been launched off in a direction. It was caught when it was 2 meters above the ground. So if you're looking at, well, we go back to the graph that we've drawn, 2 meters above the ground, right? There's a couple of possibilities you could have had. 2 meters might be, approximately here, 2 meters above the ground, or all the way over here, 2 meters above the ground. We're asked to figure out how far was the ball from where it was initially hit. So it was initially hit from here, and it's gone in this direction along the x. How might we figure out how far away it landed, or how far away it was before it was caught?
Do we find the distance? Like, do we use distance formula?
Distance formula. Let's see. Could we use distance formula for this? Tough to do it that way. In fact, maybe not doable. So the idea here is we're looking for the corresponding x values, so x being how horizontally far away it was, that corresponds to a distance, a vertical distance of 2, because it was caught 2 meters above the ground. So what that means is, I want to know, what are the x values that are responsible for giving me y equals 2? Look familiar at all?
Oh yeah, it looks like the energy question where you drew a line.
Yeah. So the challenge with these extended response questions is the way they phrase things. If you're able to do enough of these, you can break it down into very repeatable questions. Like this right now, we've seen exactly how to handle this. You sub in your y value, you get your corresponding x values, done and dusted. This question is basically identical to the energy question. It's just worded differently. And therein lies the challenge, basically. So that's why we create these sort of frameworks to figure out, okay, what is the thing we care about? In this case, we cared about distance, vertical distance. What happens when the vertical distance is 2 meters? How far horizontally would that be? Well, vertical distance 2, horizontal distance is your x. On the CAS, you can use it to find intersections. Again, I'm not really a fan of getting decimals, so I would instead just go back, chuck it in a solve, many3, 1 for solve, grab your function, in this case it was f4, and set it equal to 2, because that's our y value. Solve for x. This one's definitely going to give us a root answer, which is what you would give as your final answer. You give those 2 possible x values. You would just say meters at the end of that. If it asks for a decimal place, that's when you just hit Control Enter. And that will give you either 1.77 meters or 28.2 meters, however many decimal places they ask for. In this case, it is worded a little bit poorly. It doesn't imply that it is possible to have 2 answers. It should have implied that it was possible to have 2 answers, or at least given a wording which would cut out one of the possibilities. Cool with that?
Yep.
So if it doesn't specify the 2 answers, you automatically assume the 2 answers if it doesn't ask for only one.
Yeah, so if it's ambiguous, you give all the information. This one doesn't say decimal places, it doesn't say one possible answer, so you give the closed root form answer, both of them, because both of them are valid. Like if one of these were negative, for example, you wouldn't give that because we definitely aren't having negative possibilities. But in this case, both are positive, both are technically valid. Granted, if you think about a cricket match, you're probably not going to catch the ball on the rise. You're probably going to catch it further later, but that's not necessarily restricted from this question. the textbook questions can be a bit hit or miss. I'll say that much. They're not as bulletproof as what you'd see in an exam. I'm just sort of giving you what you would likely, or what wording would likely be present in an exam. But okay, that's that. So where's the actual? There it was. Cool. Last one is triple I. So if you go back to the screenshot with the book, at what height was the ball when it was struck? So if you just sort of bounce back and forth between the document camera and the screen share, what do we think is the answer to triple I? This is purely reading comprehension here. No math to be done.
What, 1?
Yeah, 1. Correct. Because the height was at 1 initially, right? It was struck at x equals 0. Your height at that spot was 1. Therefore, the height was 1 when the ball was struck. 1 meter specifically. Yeah. Nice and simple. Okay. And I believe the rest of these are a different kind of question. So with the remainder of the time, we'll discuss that. But for now, I just sort of want to pick out and show you what frameworks you use for what questions. So question 1 was about rectangles. Question 2, same thing about rectangles. Question 3, you handle it the same way. You're still using that graphing approach. 4, 5. Yeah, so everything 1 to 4 is using this exact same framework. You don't have to really change anything about what you do. You just have to have enough repetitions of doing this stuff to where you can do the reading comprehension side of things. Once you get over that barrier, it really is just hitting these 4 steps every time. The remainder of the questions are these so-called families of functions style questions. The whole goal there is you have some fully unknown or maybe partially unknown quadratic, and you have to figure out what all of the unknowns are in there. Like you can see this one here, ax squared plus bx plus c, at squared plus bt plus c. All of these completely unknown things. The way you handle that, more or less, is going to be grabbing the information that's given to you, plugging them into equations, and then using those equations to solve those unknowns. That's the gist of what's going on here. The challenge with quadratics is that we don't only have one possible quadratic. This is what you'd consider the polynomial form of the quadratic, or maybe the expanded form, general form. Any of those would do. But you could have a factorized form. You could have a completed square form. Each form has its advantages and disadvantages. Or I guess, well, more specifically, each form will be useful in different scenarios. I guess we'll say that much. Ideally, wherever possible, try to avoid using the top one. That's the hardest to work with. The other two, where possible, use those. Much easier. And we'll see why. You use different forms depending on what information that you have. So in this example here, we're told the turning point on our graph and some other point on the graph. Turning point at 1, 3, and this one is our y-intercept. When you have the turning point form, but when you have the turning point of your equation, use the turning point form. The reason why is because with that single point, you can figure out your, well, I've called them B and C, usually they're H and K. You can figure out what those horizontal and vertical translations are, right? This is a shift right by 1, so it's going to be x minus 1, and it's a shift up by 3, plus 3 at the end. 1 point, 2 unknowns. From there, you'll find that no matter what form you use, you'll always have this a value that you need to solve for. You will always be solving for this a by plugging in an additional known point and solving for a. So you can see the only other unknown besides y and x in this case is a. So if you were to plug in an x equals 0, a y equals 4, you will now have only a in that equation. Rearrange for a, and then you have your final equation. Any questions about that?
No.
So if you have turning point, use turning point form. Axes intercepts. If you have the x-intercept, use the x-intercept for. Again, for the same reason that you're very quickly able to solve for what those numbers are. If you have an intercept at x equals -2, the factor must have been x plus 2. Intercept at 1, 0, the factor must have been x minus 1. Very quickly solved two things. Now, granted, this is still 3 points. You could use the ax squared plus bx plus c. You'll see pretty quickly why we don't want to do that, ideally. We have our factors. A is unknown. Here's another point. Sub in that point, solve for A. Same idea. Here's the worst case scenario, or at least the second worst case scenario. The true worst case would be if you don't have a y-intercept. If you have 3 random points, you're kind of just stuck with using ax squared plus bx plus c. What that means is you sub each of these points into ax squared plus bx plus c, and you do a 3-way simultaneous equation. This one's a little bit nicer because you are told the y-intercept, and that gives you what c is automatically. You don't necessarily need to use that equation as part of your it becomes a 2-way simultaneous as opposed to a 3-way. Point, sub in, solve. Point, sub in, solve. Equation 1, equation 2. We do your simultaneous. Do I need to go into any more detail as to how the simultaneous works, or is that fair enough?
It's good.
Good? Okay. I've used elimination. A equals 2, B equals -3, and we had C equals 5. So there's your A, 2x squared, plus B, which was -3x, plus C, which was 5. So you can see, just by looking at the size of this answer versus the other two, try to use the other two if at all possible. That's how you handle that. And that is where these other questions are going to come from. So if you see example 45, we have a cricket ball being thrown again, or maybe hit. In this case, it's thrown. It's not very high, geez. Anyway, we have what is 3 known points on this graph. Now, unfortunately, we don't have the turning point or the x-intercepts. So this is one of those situations where you're doing a simultaneous. Looking at that graph, what are those 3 points? It's not super obvious. What are the 3 points?
0 to 62 and 2515.
Perfect. Yeah. Even if these aren't labeled, you can see where they appeared on the axes, and therefore they become your points. Nice. Those form the basis of your simultaneous. You can see this one got pretty nasty pretty quickly. Yeah. Sometimes you might have to do this kind of arithmetic. I know in the exams more recently they have upgraded the level of arithmetic that you will be expected to perform on. At the end of the day, it is just big numbers. Does anyone have any trouble handling large numbers like this when it's algebra? Because I have a guide that I can point you guys towards if any of that is odd. One thing I'd recommend, where is it? Review of algebra. I've used this more and more recently when it comes to solving like really big, or solving really big, or simplifying really big fractions and stuff like that. It's a method called prime decomposition. So I have this in my review of algebra chapter. It just sort of goes through a way by which you might simplify this somewhat nasty fraction into something that's significantly easier to work with. So if anyone's at all interested in that, it's in the linear chapter of the classroom. That can help you here when you've got really nasty things. Like, it's not necessarily easy to see if 13 is divisible by 875. Well, the other way around, but yeah. But okay, so as far as the questions that you might get asked to solve, question 6 is a bit of a tougher one, but it is that sort of idea. You've got ax squared plus bx plus c. There's going to be 3 points involved. I do need to show everything there because this is going to be an important bit of information. if we're thinking about the possible points here, I'll give you guys some time to think about it. What might the 3 points be on this graph?
Would A be 1.6?
1.6. Where 1.6? Oh, because 2.5 plus yeah, the difference of 2.5 and 3.1. Yeah, that's good. So that's the
And
y value of a though. You need the full point. What would be the x of a?
0.75 because it's midpoint.
Yeah, 0.75 because it's midpoint. Brilliant. That's 1 point. Nice teamwork on that one. How about the other 2 points? Where could they come from?
Is it the
intercepts at 0, 0.
0, 0. Yep.
yeah 0 and the 1.50?
1.50. Yeah. You've got this x that's going all the way in the horizontal, and there's an intercept there. Nice. That's going to be the 3 points. Sub those in. Yeah, I don't think that will be any much more difficult. In fact, because you've got 2 y equals 0s, that might almost be easier than if you had other points in different spots. Again, yeah, simultaneous. And then final question of this chapter. Again, a t squared plus bt plus c. How do you think we're going to solve for a, b, and c?
Do we just sub in like what t is like when t is 30? You just put that in there.
Yeah, those are the points just in table form. T equals 30, s equals 7.2. This is the point 150, 12.5, 300, 6. 3 points, 3 unknowns. Since these are CAS, however, has anyone done simultaneous on the CAS before?
Yeah.
Okay. Has anyone not done simultaneous? Do I need to show it?
Yes, please. I have not done it on the CAS.
Okay, that's good. So, under the algebra tab, solve system of equations, number 7. And then I choose the first one. You can choose either. I've just always chosen the first one. There's never been any issue. From here, you just set the number of equations that you need to solve. In this case, it's 3. So you're going to hit right and then up, or left and then up, whatever. Choose your variables. You could use x, y, z. To be more question specific, you might want to choose A, B, C, just so you don't like forget in the translation from the CAS to the paper. It's going to give you this setup here. Okay, one step before that actually, my bad. To save some time on how you would type this in, I would start by defining the function. So I'll do that a bit slower. Menu 1 for actions and 1 for define. I would call my generic, well, I guess you could use t. So you could even call it s of t just to be really, really consistent. And we can call that a times t squared plus b times t, and then plus c. Right, that's our function. The reason why is because I don't want to write at squared plus bt plus c 3 different times. Ideally, just write it only once. Go to the same spot, a comma b comma c. And now when we're plugging in our points, much easier, because I can just say s of 30, because t is 30 on that spot, and s is 7.2. I'll do the same thing one level lower, 150 equals 12.5, and then 300, 6. So where's s? There it is. 300 equals 6. Hit enter. That's going to give you all the solutions you need. These are exact values. If they were required in decimals for whatever reason, control enter, and that'll give you, well, a very nasty couple of numbers. But use the fractions. It's unlikely to ask for decimal places. That's your A, that's your B, that's your C. If, yeah, it's specifically asking for A, B, and C, not the actual quadratic. So this is what you give as your final answer. if it was asking for the quadratic as the final answer, then what I would actually just do is, well, you would just replace A with that, B there, and C up there. And to show you a quick way to do it on the CAS, you can use your define, grab a copy of that, kill all of this, and then when I reprint S of t, it'll have that A value in it. Do that 3 times, it'll give you the full quadratic. Okay, that brings us to end of class there. Hope that made a decent amount of sense as far as how you handle application style questions. The key things you'd want to have a read up of would be document or module 7 of the quadratics and module 1 of the linear if you wanted to have a look at how to simplify nasty numbers. Cool with that? All right, if there's no further questions, then I'll let everyone enjoy the rest of the day. Take care, guys.
Bye.